Hi everyone! In the previous videos, we learned about two IPv4 to IPv6 transition technologies, Net64 and DISLite. Today, let's take a look at another transition technology, IPv4 over IPv6. This technology connects local IPv4 networks over IPv6 networks. Why do we need IPv4 over IPv6? IPv6 has attracted wide attention because of its huge network address base, simplicity, and security. The transition from an IPv4-only network to an IPv6-only network takes a long time. The scale of IPv6-only network deployments increases toward the later stages of IPv4 to IPv6 transition, potentially resulting in some IPv4 islands. An IPv4 island is a network that is isolated from another IPv4 network by an IPv6 network. Connecting isolated IPv4 networks using private lines is costly, so tunneling technologies are often used. These technologies allow tunnels to be created on IPv6 networks, so that isolated IPv4 sites can communicate with each other through IPv6 public networks. Such a tunnel is called an IPv4 over IPv6 tunnel. So, how is an IPv4 over IPv6 tunnel established? To allow IPv4 packets to be transmitted on IPv6 networks, IPv4 over IPv6 adds IPv6 headers to the packets to encapsulate them into IPv6 packets. On an IPv4 over IPv6 tunnel, packets are processed on border nodes B and C, and other nodes are unaware of the tunnel. Specifically, IPv4 packets are transmitted between A and B and between C and D, whereas IPv6 packets are transmitted between B and C. This means that B and C must be able to process both IPv4 and IPv6 packets. That is, both border routers must run IPv4 and IPv6 dual stack. An IPv4 over IPv6 tunnel is manually configured between border routers. You need to statically specify the source addresses or interfaces and the destination addresses or destination domain name. The destination address of the local tunnel must be the same as the source address specified by the peer tunnel interface. In addition, the route to the peer interface that receives packet must be reachable. After the preceding configurations are completed, an IPv4 virtual link is established between B and C. Through this link, B and C can advertise routing information. To ensure packet forwarding, you can use static routes or dynamic route protocols such as IGP and BGP to advertise routing information. To configure a static route, you need to specify a destination address and a next hop on both ends of the tunnel, namely B and C. The destination address should be the destination IPv4 address of the original packet, and the next hop should be the peer tunnel interface. To configure dynamic routes, you need to enable a dynamic routing protocol on the tunnel interfaces and IPv4 network interfaces of B and C. B and C then use dynamic routes to advertise routing information and both establish IPv4 and IPv6 routing tables. Taking OSPF as an example, the IPv4 routing table of B contains routing information in which the destination address is D. The next hop address is the tunnel interface address of C, and the next hop should be the peer tunnel interface. Next, let's look at how packets are forwarded over an IPv4 over IPv6 tunnel. IPv4 packets are transmitted through an IPv4 over IPv6 tunnel in the following phases. First, IPv4 packet forwarding. A sends an IPv4 packet to the border node B, with the destination IPv4 address being the IP address of D. Second, tunnel encapsulation. After B receives the IPv4 packet from A on the IPv4 network, B finds that the destination address of the IPv4 packet is not itself, and the outbound interface to the next hop is a tunnel interface. B then adds an IPv6 header to the packet. B encapsulates its own IPv6 address into the source address field, and the IPv6 address of the peer border node C into the destination address field. Third, tunnel forwarding. B searches the IPv6 routing table for an entry matching the destination address of the IPv6 packet header and forwards the encapsulated IPv6 packet to C. Other nodes on the IPv6 network are unaware of the tunnel and process the encapsulated packet as an ordinary IPv6 packet. Fourth, tunnel decapsulation. Upon receipt of the IPv6 packet, C discovers that the destination address is its own address, and the original packet is an IPv4 packet based on the next header field. It then decapsulates the IPv6 packet by removing the IPv6 header based on the version field. Fifth, IPv4 packet forwarding. C searches its IPv4 routing table for an entry matching the destination address of the IPv4 packet and forwards the packet to D. To sum up, unlike IPv4 and IPv6 dual stack, IPv4 over IPv6 uses an IPv6 tunnel as a virtual IPv4 link. The existing networks do not need to be reconstructed, and devices on a backbone network do not need to be upgraded. In addition, only border devices connecting IPv4 and IPv6 networks need to support dual stack and the tunneling functions because other devices are unaware of the tunnel. Moreover, IPv4 over IPv6 is easy to deploy. However, IPv4 over IPv6 has some limitations. This technology provides only a point-to-point transparent transmission channel. In this case, IPv4 hosts cannot directly communicate with IPv6 hosts. Furthermore, manual configuration is required, resulting in high network maintenance costs. And a large amount of tunnel data needs to be maintained, increasing network overheads and potentially affecting network quality. Fortunately, these problems are eliminated once the network evolves to an IPv6 only network. With the support of IPv4 over IPv6, we expect the transition to IPv6 only networks to be a quick process.